Welcome to Operating Systems lecture 32, and we're talking about file system implementation. And yesterday, or in the last lecture, we were looking at on-disk data structures, which is basically the file system is nothing but an on-disk data structure, and we looked at two options. One was a contiguous file system, where contiguous allocation, where a file or an inode is defined by or stores a base and a length, and that's where your file resides. The advantage of that is that contiguous bytes in a file are also contiguous on the disk, so it makes for very fast sequential access of the file. The bad thing about that is fragmentation and growth, right? So this is similar to what we saw with segmentation in virtual memory. It has those problems. The other on-disk data structure we looked at was a linked list, which we said that lets the file or inode contain a pointer to the first block, and then each block has a 4-byte next pointer. This gets rid of the problems of fragmentation and also growth. Growth is very easy, fragmentation is no problem, but it is very, very slow, right? It's slow not only because of sequential access, because for sequential access you have to just keep seeking, because the file blocks will be strewn across all around the disk, but it's especially bad for random access. You have to actually traverse the entire linked list to get to any block in the file. Moreover, recall that our magnetic disk has this problem that it's better to give lots of IOs in flight simultaneously, right? Recall that the disk controller is doing some scheduling internally, and so it'll be best for the OS to have lots of outstanding IOs for the disk, so that the disk can schedule them in the most optimal way. But if you have a linked list allocation, then and you are traversing the linked list, you can have at most one IO in flight at any time, right? Because you have to wait for the first IO to finish and get the data before you get the next pointer, and then you issue the next IO. So there can only be one IO in flight, and that's a really bad thing from a performance standpoint. And the third thing we said was bad about it was basically reliability. So one link goes bad or one block goes bad, the entire file gets corrupted. Okay. So let's talk about some more realistic file systems, and one successful idea has been what's called FAT, or file allocation table. Yes, question.
So for the thing that you said, that if one block gets corrupted and the whole file gets corrupted, so don't you think that simple techniques like making a double linked list and storing both the head and the tail can reduce the probability too low?
Okay, so here's a suggestion that instead of using a singly linked list, as I said, let's have a doubly linked list, and that would improve reliability by some degree. But really, would it? I mean, if you just firstly, it has all those problems of being slow, right? So that's that's one big con of this. The other thing is, even if you have a doubly linked list, if one block goes bad, then the next pointer is gone, and the previous pointer is gone. So I don't see how.
I store the pointer of both the head and the tail, so in my inode.
Okay.
So I can reach.
I see. So you're basically saying that inside my inode, I could just store the pointer to my inode, let's say. For each block, I could store a pointer to the inode, and so I know that these blocks belong to this inode.
No, the pointer to the head of the doubly linked list and the tail of the doubly linked list. So means the probability that the two blocks of the same file gets corrupted is too low. So means
he's saying like if a block is corrupted, we can travel from tail.
Okay, I see. So if a block gets corrupted, then you can travel in the reverse order. You can travel from the tail, and you can organize your data structure so that if two blocks get corrupted, then the file gets. Yes, it's a valid thing. You could do that, but yeah. So you could solve the reliability problem by adding more to this linked list idea, but I mean it's bad anyways, right? It's bad because of performance reasons. Okay, so here's a very nice extension to the linked list idea, which is file allocation table, first used in MS-DOS, which was basically the idea is that maintain this linked list not in the blocks themselves, but have a separate file that maintains this linked list, right? So have a file which you will call the file allocation table, right? So this is the file allocation table, or FAT, and this has all these entries for each block, right? And now inode just points to, so inode points to the head pointer, which points somewhere here, and within this file you have pointers like these, right? And so if you want to go to, so a file basically points to some entry here, and that entry says that the first block, it contains the block ID, right? So block ID or block number of the file and on the disk, and so you can read that block. So that's the first block, and if you want to get to the second block, you chase the pointer from here, right? So let's say if you wanted to get to the nth block, you need to do pointer chasing within this table. You don't need to actually fetch the real blocks, you only need to do pointer chasing within this table. And the idea is that if this table is small, it can be brought into memory in one go, and then this pointer chasing can be done completely in memory, right? And so if you can do the pointer chasing in memory, then you have eliminated much of the problems of the linked list allocation that we had before. Okay, so let's see how big does this file need to be. Well, for every block we'll have one entry.
So block is a sector.
Right. So what does a block mean? A block could mean one sector or some small multiple of sectors, right? So maybe 8 sectors or 16 sectors. The MS-DOS block size ranged between 512 bytes to actually, or 2 kilobytes for the FAT32 system to 32 kilobytes. Right. So a block could be anywhere between 2 kilobytes and 32 kilobytes. The block size needs to be decided at the time of format, right? So a disk partition will have a constant block size throughout the life of that partition, right? And so depending on the block size, you will basically name the disk blocks, right? And so each entry here needs so the first incarnation of this idea was in the FAT16 file system, and the reason it was called FAT16 was each entry was 16 bits, right? So each entry was 16 bits, and a block could be between 2 kilobytes and 32 kilobytes. So what's the maximum size of a disk that you can support? You could have at the most 2 to the power 16 blocks in your disk, and each block being, let's say, 2 kilobytes. So if the entry size is 16 bits, the maximum size of the table can be only 2 to the power 16, right? That's the number of unique blocks that you can address. And so that's 2 to the power 16 blocks, and into the size of the block. So let's say it's 2 kilobytes, then that's roughly 2 megabytes and 64 megabytes, or 128 megabytes, right? Let's say the block size was 2 kilobytes, and you have a 16-bit entry in your file allocation table. You basically have a 128 megabyte disk that you can support with this organization. So just to make sure that everybody understands this, let's say I have another file. So let's say this is A's inode and this is B's inode. Then B's inode will point somewhere else, and then it will have its own linked list to follow, right? And one block will only be part of one linked list. So one block can only be part of one file. There's no sharing between files of blocks, of course, right? So for so the FAT16 file system with the 16-bit thing could support a disk of at most 128 MB. Doesn't seem very large by today's standards, but at that time it was a reasonable size given the technology of that time, right? Roughly late 70s, early 80s. And what's the size of my FAT16 table? 2 to the power 16 entries, each entry being 16 bits. So that's what, 2 into 2 to the power 16, right? That's 2 to the power 32, or 2 to the power 17. That's 128 kilobytes, right? So 128 kilobytes. At that time, memories were typically bigger than 128 kilobytes, and so it was a reasonable scheme to have. Okay, all right. So, but it doesn't make sense in today's technology. So so it was extended to what's called FAT32 today, and FAT32 had, instead of 16 bits, 28 bits for each entry, and it supported block sizes between 2 kilobytes and 32 kilobytes. And with this, you can have a maximum file size of 512 gigabytes. So let's say you have 2 to the power 28 entries. What's the size of, how big is fat? 2 to the power 28 into 4. Let's say each entry is 4 bytes. That's 1 gigabyte, right? And how big can the disk be? To the power 28. Let's say I was using block size of 2 kilobytes. Then I have 2 to the power 28 into 2 kilobytes. That's equal to 512 gigabytes. Right. So you can support a maximum size disk of 512 gigabytes with the FAT32 file system with a block size of 2 kilobytes. If you want to have a larger disk, one straightforward thing to do is increase the block size. Right. So you could take it up to 32 kilobytes, and that way you can multiply this number by 16. So what's the and once again the block size is decided at format time and just remains constant for the life of that disk partition. So what's the advantage of having a small block size versus a large block size? What are the trade-offs? What are the trade-offs involved? One clear trade-off is the larger the block size, the larger disk you can support. But what are the other problems? Firstly, there is what's called internal fragmentation. So I was interested in let's say 16 bytes of the disk, but I have to read the entire 32 kilobytes, right? So there is more extra things that you may need to read into the memory, right? You need to maintain the buffer cache in that way, and also you so that's one thing. So you need more time for the data transfer. Also, you pollute a buffer cache. So the more data you bring in, the more data you need to evict. And if that extra data is not really useful, then you are polluting your buffer cache. The flip side of it is the larger the block size, the more spatial locality can be exploited, right? So it's really a trade-off between spatial locality and internal fragmentation. So the larger the block size, assuming your program has a lot of spatial locality, a better thing to do is to have a larger block size. On the other hand, if it doesn't have that much spatial locality, the smaller block size would have performed better. All right. Okay. What is the space overhead of a fat file system? So if I were to say, space overhead of a file system, I basically say amount of metadata divided by amount of real data, right? So how much metadata is stored per unit of real data in this file system? Well, I'm storing, let's say, 4 bytes per 2 kilobytes. Let's say I'm using a 2 kilobyte block, then that's roughly 0.2%. Right? So that's not too bad. That's the space overhead of this file system. Okay. What about reliability? So let's first talk about efficiency. Right? So what were the few things that we were concerned about when we talked about efficiency? Number one, we wanted to say how good is sequential access. So let's say I wanted to read the file sequentially from some x to x plus 100 or whatever, and so what should the speed be? Well, in contiguous it was great. What do you think? In linked list it was very bad. What do you think about FAT? It's better than linked list? Definitely better than linked list, because you can compute in memory the list of blocks that need to be read a priori. You don't need to wait for blocks one by one, right? So you know the exact 100 blocks. These 100 blocks may be strewn across the disk, so they may not be contiguous necessarily, but you can give 100 blocks in flight to the disk. So you can have 100 outstanding I/O simultaneously, and the disk scheduler can schedule those 100 blocks efficiently and give you much better performance than the linked list allocation. But it's not as good as the contiguous allocation, of course, because the contiguous allocation would have just used one seek and one latency, and the rest would have been the data transfer time. Here you will have multiple seeks and multiple latencies, but at the same time, because you have so many outstanding I/Os, the effect is amortized. Right? the disk scheduler can schedule things properly. What about random I/O? Let's say I just want to say get to the offset X in a file. Is it fast or is it slow? It's as fast as it can be, right? Assuming that the file allocation table is in the memory, you just chase the pointers inside memory. You figure out what disk block you want to read, and then you issue that request. And that's the minimum you need to do, anyways. Yes, question.
We said about corruption of a block.
Right. Okay. Good. So that's efficient. So I've talked about efficiency. Let's talk about this is time efficiency, of course, and then let's talk about reliability. Right. So these are some parameters we are sort of evaluating our file system design on. So is it reliable?
Yes, provided memory is reliable.
Okay, here's an answer, provided memory is reliable. No, we are not talking about reliability in terms of, we are talking about reliability in terms of durability of data. So we expect disks to live for multiple tens of years, if not more. And so if disks live for that long, the probability that one sector in the disk gets corrupted is very high, relatively high, right? But we also want, and the idea of using disks is that the data remains durable across tens of years, let's say, right? So is it possible that one disk block gets corrupted and that causes lots of data loss in this organization? Well, if the fat block gets corrupted, so after all the fat is also getting stored on the disk, right? So if the fat block gets corrupted, then yes, you will basically suffer a lot of data loss. So what's one easy way to fix it? Have multiple copies of the fat, that's all, right? So have multiple copies of the fat. I said 0.2% overhead, now it will become 0.4% overhead, space overhead, but you'll have significantly higher reliability, right? So that's easy. So typically you will have multiple copies of 2 copies of the fat on your disk to ensure reliability. Yeah, question.
Sir, when we copy something or write something, we will have to update that, right? On the table.
When we copy something or write something, we have to update the table. Yes.
But it can get corrupted around that.
Right. So when I talk about reliability, I'm talking about of a stationary disk. All right. So what happens if what happens while the program is running and some crash happens? That's not going. I'm not going to call it reliability. I'm going to call it durability guarantees of the file system, and we're going to discuss that very soon. Okay. But when I'm talking about reliability, I'm talking about stationary disk and what's its reliability.
So
Yes.
for FAT32, we can't keep the whole FAT table in memory, right?
For FAT32, we cannot keep the whole fat table in memory, but yes, so of course you don't need to keep the whole fat table in memory. There is some caching that you can do there also. So you can treat the physical memory as a cache for the fat table itself. Right? And assuming there is locality of access in the fat table, the cache should have a very high hit rate. Okay. All right. Okay. Finally, how do you bootstrap the system? So in general, for every file system, so let's say bootstrapping. So by bootstrapping, I mean how does the OS know where the fat lives, right? Once it gets to the fat, then it knows where all the files live. That's no problem. But how does the OS know where the fat lives? Well, one typical way to do that is, let's say this is the disk, and the 0th sector, recall, is the boot sector. So we don't use that for the file system at all. Okay, the boot sector is completely independent of the file system. It has nothing to do with the file system. Recall that the boot sector actually contains instructions that need to be executed at boot time. So it has nothing to do with the file system. And the first block is assumed to have some. It's called a super block. And this block contains information about the fat. Let's say. So here's the fat. Let's say. Right. And then the fat has pointers to everything else. Okay. All right. Okay, so fat is actually a real file system that you use. The other type, another type of file system is called what's called indexed file system. Right, and the idea here is simple. In the fat file system, we had the inode point to the head or the first block of the file. In an indexed file, inode contains an index, right. So here's an inode and it contains many rows and it has an index and so on, right. Basically saying that the first block of the file is at this location, the second block is at this location and so on, right. So this is an indexed file. So you have more information in the inode, and so once you read the inode into memory, then you can get to all the blocks of that memory, of that inode. Okay. So this is an alternate organization, you just have an index over the thing. So let's see what are the pros and cons of this.
This index lives on disk only.
This index lives on disk, yes, definitely.
But
These are all on disk data structures.
But when we are accessing the file, we first bring this whole data structure into the memory and then.
Right. So now if I want to access a file, and the inode, so this is called the inode, right. This index is stored in the inode. So the inode needs to be brought into the memory, and then you will look at the index to get the block, right. Assuming that the inode was previously cached, you take only one disk access. If the inode was not previously cached, then you take two disk accesses, one for the inode and one for the disk block, right. It's not very different from the FAT file system also, you cannot, it's not possible to store the entire FAT in memory, or you may not want to store the entire FAT in memory all the time. So sometimes you may take a miss on the FAT itself, right. So that it's very similar to that. Okay, so this is an index file system. So what's the problem? Firstly, how big can the index be, right. So how big can the index be? You would want that the index is not bigger than the block, right, or the inode is not bigger than the block. And so let's say your block size is block size, let's say, then block size divided by entry size, and let's say entry size was, so divided by entry size is the size of your index, right. And let's say typical block size is, let's say, just take an example, let's say 512 bytes, and entry size is 4, then you have 512 by 4, that's 128 entries. And so what does it mean? It basically means that there's a limit on the maximum size of a file that you can have, right. So what's the maximum size of a file you can have? You have 128 entries into a block size of 512 bytes, that's roughly 128 into 512, that's 64 kilobytes, right. Okay. So index files look good, but for example, for a block size of 512 bytes, I can only have a file size of 64 kilobytes. A block size of 2 kilobytes will increase this number by a factor of 4, but that's not good enough, right. So it's not great because unless I increase the size of my inodes, so it's a trade-off between the size of the index and the size of the file. So the larger the index you can support, but that also adds to space overhead. So what's a better thing to do? This is a one level index. One level index can only grow to that, one level index can only point to that much data. So you want to have a two level index. That's one way of, we all studied things like trees in our data structures course. But if you have a two level index, then the trade off is that I have to make two disk accesses before I actually get to the block. So actually 3 total disk accesses. So it's not, and is given that most files are small, right. So most of the files in your file system, if you think about it, are executables, which are roughly few kilobytes in size, or configuration files, which are just small text files, or code files, .c or .h files or .java files. These are also relatively small files, few kilobytes. And so I want to optimize for the common case, which is lots of small files, but then I have some files that are really large, right, like log files, which run into megabytes, hundreds of megabytes, or even gigabytes, right. So my typical workload or file distribution, size distribution is lots of small files, some very large files, okay, and I want to optimize for that. So instead of having a uniform 2-level structure, what's done is you have a multi-level index. Right. What this means is that the first few entries are single level, then few entries are actually double level, which means they point to other indexes that point to more more blocks, and then the last entry or last few entries are actually triple level, or actually this is called double level, yeah. So and then there's triple level, which means it's a 3-level hierarchy. Okay. So what you have done is that for the common case that you have small file, you have only one access, one metadata access, and for the other common case, which is very large files, small number of large files, you will have to make 2 or 3 metadata accesses, but those accesses are likely to get amortized over a large number of blocks. Right? After all, that was a large file, so you're going to probably access a lot of blocks in that file if you are accessing it. Right? So let me draw this again. This is a multi-level indexed file. Right. So let me take the example of a real operating system, 4.3 BSD Unix, and let's look at its file system structure. It uses multi-level index file. inode contains, so this is the inode. It contains 14 single 14 single level pointers, each 4 byte. Right. Next entry contains one doubly indexed pointer or indirect block. The other way to call it, so instead of calling it double level, I'll call it one indirect. So these are direct pointers, and one indirect pointer that points to an index with 1024 direct pointers. All right. And last index, so this is this one entry, and then last entry points to one doubly indirect pointer. Right. So by doubly indirect I mean it points to a block that contains pointers to more indirect. So it's a 3-level hierarchy, right? So it's a 2-level hierarchy from here on. Here there's a 1-level hierarchy, and here these are direct pointers. Okay. So with something like this, you have optimized for the common case, which is that small files. So small files of size less than, let's say my block size was 512 bytes, then files of size 14 into 512 bytes, that's 7 kilobytes. So files of up to size 7 kilobytes will need only one metadata access to be referenced. Right? Files of size, so one indirect pointers with 1024 direct pointers. So that's 1024 into 512 bytes. So that's 512 kilobytes. So files of size up to 512 kilobytes will need 2 metadata accesses to be able to dereference them, and then files bigger than that, which will be 512 megabytes or larger, can be done using 3 metadata accesses. So that's basically how it's done. Right. Still you have a maximum size limit on the maximum size file you can have. So every file system will have some limit on what's the maximum size of a file that you can have, but all you are doing is just making that limit really large. Right? And depending on the current technology, that may suffice and or may not suffice, depending on what you do. Right? Okay. For example, for a long time Linux didn't support files larger than 2 gigabytes, right? For example, I remember till early 2000s, Linux wasn't supporting files greater than 2 kilobytes, but then, future versions of the file system basically allowed bigger files and so on. Right? So depending on the hardware technology, you will basically revise this as it goes. All right. Okay, so that's basically the file system structure. We have looked at the fact file system, which is an in-memory linked list, and then there is an index file system, and both are widely used. Index file system is used in Unix, and also the NTFS file system is an index file system, and the fact file system is also, by its name, called fact file system. Now, one of the things that you have to worry about in a file system is what happens on a power failure or a crash. You're in the middle of doing something and a crash happens, and then you come back again. Your things may not be in a consistent state. How do you deal with that, right? So one way to deal with that is that you don't worry about it at all, right? You just say, if a crash happens in the middle of something, then at reboot time I will run a program. For example, the Linux or Unix systems have this function program called fscheck. So you run the fscheck program gets to run on a reboot, and it will do a global scan over your file system and see if it finds something wrong. And sometimes it may not be able to automatically decide whether what should the fix be. So if it finds something wrong, what should the fix be? It may not be able to automatically decide, so it may need to actually ask the user, and it's a very painful decision procedure for the user to figure out what happened and what should be the right thing to do. And we're going to look at what kind of questions can come up and what kind of things that can go wrong. Right. The problem with this, the nice thing about this is that in the common case when there's no crash, things can work at full speed and very simply, no problem. The bad thing about this is that the fscheck program can take a long time. In the early days, 90s, disks used to be small, so a global scan was possible in a few seconds, maybe tens of seconds or minutes. But with disk sizes of 512 gigabytes to 2 terabytes, these disk times can easily take up to half an hour or 1 hour or maybe more. Okay, so that's a cause of concern. And so this technique, while was used for a long time in real operating systems, is no longer used, and some other things are used. The other so that's one thing. The other thing to do is basically say that I will ensure that so there's something called journaling, and we're going to discuss what it means. So journaling basically ensures that your updates to the file system are atomic with respect to the power failure. Right, so there's a way to ensure that updates to the file system are atomic with respect to power failure. So if a power failure happened in the middle of an operation, then it's as though the operation never took place. All right, so that's you maintain a data structure that ensures that an on-disk data structure that ensures that it doesn't take place, and if it happens after the end of this operation, then the operation so either the operation has taken place in full or not at all. So that's atomic. So one thing is journaling everything, which means you journal both the metadata, which is these inode structures that you have, and the data of the user. That will provide you very good guarantees of over atomicity, and the user can be sure that whatever he's doing is correct. And the other option is to journal only metadata. Right? Here you're saying that I will basically make sure that my metadata or the inode structures and other things that I'm using for my file system remain consistent across power reboots, but the user's data may become inconsistent. Right? It's something similar to killing a process. Right? When you kill a process, you make sure that the kernel side of state is cleanly freed. Right? Recall that you don't just free the process, you just wait for the process to reach some clean boundary before you actually free it. But at the same time, there's no guarantee for the user. Right? The user could be in the middle of something and he can immediately get vanished. Right? So and the user should expect that. Right? So that's the other approach, which is you journal only the metadata. Okay, and we're going to discuss this again. The other thing you have to worry about is, of course, efficiency. So how do you provide efficiency? Well, firstly, data structure design that we have already discussed, and this is basically about minimizing seeks. Right? So some things that can be done here is locality. Right? So by locality I mean try to place blocks, consecutive blocks of the file consecutively on the disk, because assuming that the file has spatial locality, it will directly translate into spatial locality on disk, and so you will reduce the number of disk seeks, right? So for example, your disk defragmenter program that you may have seen in some operating systems will try to improve locality to give better efficiency for your file system, right? Then intelligent indices, right? And examples, multi-level you have seen. There could be, you could use B trees and choose. So B trees with carefully chosen values of B can basically optimize performance, because your B can be tuned to the size of your block on the file system, right? So if you carefully choose B trees with the carefully chosen Bs, then you can optimize these things, and databases use this a lot. And the other way to minimize seeks is what's called logging. So here the idea is that try to make writes to the disk as sequential as possible, right? So instead of let's say I wanted to write 10 different files at the same time, and these files are completely strewn across the disk. So instead of going to each file separately and writing to them, could I organize my data structure such that all these writes appear as a log, and so it becomes one sequential write, and that's what gets written to the disk, and asynchronously it gets updated on the real file system, okay? And so using that, you can basically minimize the seeks required on the fast path, which is when you're waiting for the disk to finish. So you can just log the data onto the disk in one go and asynchronously transfer it to the file, and then we're going to look at examples on how to do this, okay? The other thing you can do is prefetching, of course, right? So you read some data, you have some algorithm which basically figures out that there's a lot of spatial locality, so you prefetch data. Of course, there's a trade-off about how much to prefetch and how much you cannot prefetch, and overlap computation with disk access. It's a good idea to while you're doing the disk access, to also keep computing, so that firstly you'll keep your CPU busy, and secondly your computation may lead to more disk accesses, and that may lead to better disk scheduling overall, right? Okay. All right, so we're going to look at so these are the basic sort of design principles on which we're going to decide what is a good file system and what's not a bad file system. But let's first start with a simple file system, which is the x86 file system, and let's look at a realistic implementation of a very simple bare bone file system, right? Okay, so here is the x86 file system. Let's say this is my disk, and this is block 0, that's the boot sector. This is block 1, that's the super block, right? And then from block 2 to some number, they have inodes. Okay. Then till some point they have what's called a free block bitmap, and then you have the blocks themselves, right? So let's look at it. So the first two sectors are clear, boot sector and super block. The next few sectors are reserved for inodes, which basically means that all inodes will be allocated from here, right? So that basically immediately puts a restriction on the maximum number of files that you can have in your system, right? One advantage of putting all the inodes together like this is that often you may want lots of locality between your inodes, right? So let's say you are doing ls, right? So ls basically wants to look at all the files in a directory, and all it cares about is things like last modified time and some characteristics that can be just you don't need to look at the data blocks, you only need to look at some statistics about that inode, right? And so if lots of inodes are being read, there's a lot of locality between the inodes, and so you can service a lot of requests from here. right. But on the other hand, conversely, you also expect there to be a lot of locality between inodes and data blocks, right. It's also quite likely that when you access an inode, then you're going to access the data block corresponding to that inode. But this organization does not exploit that locality, right. So there's a trade-off. Then there's a free block bitmap, which basically says which of these blocks are free. So it's basically maintaining a list of free blocks, right, and basically using 1 bit per block, indicating whether that block is free or not. Okay. Once again, you expect that this free block bitmap is a very sort of hot region, because if you're creating or deleting a lot of files or and so on, or writing to a lot of files, then you probably need to have this, and so it's good to have this in a very local way. So there's a locality in free block bitmap. Okay. Right. Let's look at the inode structure. So they use indexed files. Right. And the inode structure has 12 direct pointers, right, and 1 indirect pointer. Okay. Block size is 512 bytes. Indirect pointer points to a block with 512 divided by 4, that's 128 pointers. Okay. Notice that the inode itself has only 12 pointers, 12 plus 1, 13 pointers, whereas the indirect block can have more pointers. Why? Well, the inode has also extra information to store, like things like what the permissions are, who owns it, or what's the last modified timestamp, and other things, right. So there's more information in the inode, so that takes up some space. So you have only space left for 13 pointers in the inode, but in the indirect block, you have the whole space available for pointers, right. So you can calculate what's the maximum size of a file that you can have. You can have 12 into 512 bytes plus 128 into 512, right. That's the maximum size of a file you can have, roughly 64 kilobytes. Okay. All right. Okay. So what about directories? How are directories implemented? Directories are nothing but files, but special. They're special in that the user cannot read them directly. It's the operating system that can read it, right? And it's only the operating system that can interpret it, right? So directory is a file with records, so directory entries. Right? And on XV6, it's represented as an array of directory entries. So for example, if you have a directory, let's say you have a directory called /foo, then /foo will point to an inode. There will be some status flag in the inode which says I am a directory, right. All other files will have the status flag saying I am a file, but a directory, so there will be a bit which say distinguish between files and directories. And then just like everything else, it will have pointers, direct pointers. So these are data blocks, but these data blocks will contain directory entries, right. So basically a directory is nothing but a file which stores directory entries in them, right. And directory entries on XV6 are represented by a structure which is fixed size structure, which contains two fields, name and inode number. right? So a directory entry contains two fields, the name of the file or the directory, right? So this name could be the name of a file or a nested directory, and the corresponding inode number. Okay. And XV6 says, I'll only allow names up to 14 characters long, so you have a fixed size on how big the name can be. And inode number is fixed, and so there's a fixed size structure of directory entries, and that's basically used to implement directories. So what's the maximum size, or what's the maximum number of files you can have in a directory? Let's say my directory, so the maximum number of files I can have in a directory is basically is what? Max size of file, which we computed earlier, which was, let's say, 64 kilobytes on XV6, divided by size of directory entry, right? Let me call it dirent, dirent. So that's basically the maximum number of files you can have in a directory, right? Whatever the maximum size of file you can support, that's the amount of space you can have for storing directory contents, and so you can have that many entries inside a directory. Okay. So if I were to draw a diagram, let's say this is slash, so that's the slash directory, the root directory, that points to an inode. And these point to different, so these have, the name can be, let's say, slash user, it's pointing to another inode. So these point to data blocks, right? So the inode themselves point to data blocks. Let's say the slash directory has only 10 files, and the 10 files can fit in one data block, so you only have one data block, all the others are 0, right? And this data block will have directory entries which will be mapping names like slash user to inode numbers, right? And they themselves may be directories, which means they themselves may now have this structure within them, or they may be files, in which case these data blocks don't have any special meaning, they are something that the user has defined. Okay. All right. So let's look at the XV6 inode structure once in detail a little bit. You have a type which says whether it's free or directory or file, right? You have nlink, which says how many inward links do I have, right? What's the size? The size basically means what the size of this file for a file, and for the directory it basically means the number of directory entries into the size of the directory entry, right? So in both cases, size basically means the size of the data blocks, or the size of the useful content in this file or directory. And then you have the addresses or pointers, recall the 12 plus 1 thing, right? Direct and indirect. Okay. So let's say I wanted to create a file. So let's say you want to create a file on XV6, and let's say you did that using this command called echo greater than a. So what happens, just as a recap, you're running the shell process, you type this command, it calls fork, it calls exec echo, echo program gets to run with its output redirected to the file A, right. Now before but A, let's say, does not exist earlier, so the first thing the program needs to do, the shell program needs to do, is to create the file A, right. So let's look at, from a disk perspective, what all needs to happen for the file to get created. Okay. So let's look at this figure. I want to create a file A. So first I will allocate an inode. Right. How will I allocate an inode? I will go through this list of inodes and find the first one that's free. Okay, so that's allocating an inode. So that's one disk access. And once when I allocate it, I'll also mark it as a file. Instead of a free flag, I'll mark it as a file flag. Okay. Then I will update the inode with size 0. Right. So you've allocated an inode and you will update the inode with size equal to 0, and you may want to update other things like nlink, etc. For example, now there's a directory that's pointing to me, so you want to increment the nlink of this particular file. Okay. And you may also want to zero out all the direct and indirect pointers. So so that's another disk access. You could have potentially combined the first two disk accesses if you are being smart about it. Then you add entry for A in parent directory. Right. So how do you do this? Assuming that you basically look up the parent's directory's file, and so the file contents are going to live somewhere here, and there you basically append to the directory's file and another directory entry which has name equal to A and inode number equal to whatever you allocated, whatever you found earlier, right. So that's another disk write. So I'm actually just counting the number of disk writes. I'm not counting the disk reads at all here, right. You may actually need to go through the directory's inode and the directory's data blocks to basically get to that point, and then you update the directory's data block. So in this case, the updation of the directory's data block means adding or appending to its contents. So what's the last thing you need to do? Update the size of the directory, right. This you have appended to the file of the directory, so you need to update the inode of parent directory. Particular size, right. So at this point you have created the file. You have allocated an inode, initialized it, created a mapping by appending a directory entry to the parent directory, and updated the size of the parent inode. Okay, so many disk accesses for one operation. All right, so. Right, so let's stop here, and we are going to continue this this method of looking at what happens on a file operation, and in particular we are going to look at what happens if multiple processes concurrently try to write to the same file, for example, or how does data get appended to a file, and how do files get removed from a directory. So what are all the operations that need to be done to do this. Okay, thanks.